Hey friend, if you want to relax and fall asleep, this is the right place. Tonight we'll visit the universe inside the atom. The quiet nucleus, the forces that hold it, radioactivity's steady glow, and fusion that lights the stars. Dim your screen, lower the volume, breathe slowly. Welcome, especially if you're new here. Let's begin. Chapter 1. What is nuclear physics? Nuclear physics is the study of the atomic nucleus, the compact, positively charged heart of every atom where nearly all of its mass resides. While chemistry deals with how atoms bond and interact through their outer electrons, nuclear physics looks inward, asking how protons and neutrons arrange themselves, what forces bind them, why some combinations are stable while others decay, and how changes in the nucleus release energies millions of times greater than ordinary chemical reactions. It sits at a crossroads. On one side, it touches particle physics, which probes the quarks and gluons inside nucleons. On the other, it merges with astrophysics, explaining how stars shine and how the elements in your body were forged. It also extends into medicine, energy technology, geoscience, and cultural heritage, offering both practical tools and profound insights about matter itself. The field began in the early 20th century, when experiments showed that atoms were not indivisible billiard balls. Rutherford's scattering experiments revealed that nearly all atomic mass and positive charge are concentrated in a tiny nucleus, far smaller than the atom itself. This discovery raised enduring questions. What holds the nucleus together against the electrical repulsion between protons? Why do nuclei appear in many different forms called isotopes? Why do some nuclei decay spontaneously while others remain stable for billions of years? These questions define the new science of nuclear physics. At the scale of the nucleus, the building blocks are protons and neutrons, collectively called nucleons. An element is defined by the number of protons it contains, while isotopes differ in their number of neutrons. The nucleus is a quantum system. Its properties are governed by wave functions, discrete energy levels, and tunneling phenomena. Nucleons interact through a strong short-range force that is a residual effect of the deeper force binding quarks. It is strong enough to overcome electrostatic repulsion at distances of a femtometer, yet it rapidly falls off, allowing nuclei to have surfaces and sizes that scale with the cube root of their mass number. Inside, the arrangement of nucleons is not static. The nucleus exhibits both collective behaviors, tiny vibrations and rotations, and single particle behaviors, where nucleons occupy shells analogous to the electron shells in atoms. These nuclear shells explain why certain magic numbers of protons or neutrons confer extra stability. In parallel, the liquid drop picture treats the nucleus as a drop of quantum fluid with surface tension and deformation energy. The coexistence of both models highlights a theme. Nuclear physics often requires multiple perspectives to capture the full complexity of this quantum many-body system. One of the most striking aspects of nuclei is the existence of binding energy. The mass of a bound nucleus is slightly less than the sum of its free protons and neutrons. That missing mass corresponds to the energy required to separate the nucleus, or equivalently, the energy released when it forms. This principle underpins nuclear power, stellar fusion, and radioactive heating in planets. When nuclei rearrange themselves by fission, fusion, or decay, they move toward lower energy configurations, and the difference appears as kinetic energy of particles or high-energy photons. Radioactivity is the spontaneous transformation of unstable nuclei. In alpha decay, the nucleus emits a helium-4 particle. In beta decay, a neutron converts into a proton or vice versa, emitting an electron or positron and a neutrino. In gamma emission, an excited nucleus releases a photon without changing its composition. These processes are governed by quantum mechanics. For example, alpha particles escape by tunneling through the potential barrier. Because decays are probabilistic, the exact moment cannot be predicted, but a half-life describes how long it takes for half a sample to transform. These half-lives span from fractions of a second to longer than the age of the universe, revealing the diversity of nuclear stability. Beta decay highlights the role of the weak interaction, one of nature's fundamental forces. It violates certain symmetries, including left-right parity, and produces elusive neutrinos. These particles, almost massless and rarely interacting, are essential to nuclear astrophysics. They stream from the sun and supernovae, carrying away energy and offering clues about processes otherwise hidden from view. Detecting them requires huge, shielded detectors, but when they are captured, they provide a direct line of evidence about nuclear reactions in stars. Nuclear reactions occur when an incoming particle collides with a nucleus. These can be elastic, inelastic, or transformative, creating new isotopes or triggering fission. Their probabilities are expressed as cross-sections, measured in barns, an ironic term for an extremely small area. Reaction cross-sections often show resonances, sharp peaks at certain energies that reveal the quantized internal structure of nuclei, much like the resonances of musical instruments reveal natural modes. To study these processes, physicists use accelerators to create beams of protons, heavy ions, or electrons. Targets can be thin foils of stable elements or exotic, short-lived isotopes created moments before use. Detectors register particles and photons, converting their interactions into signals that can be analyzed. Advances in detectors allow precise measurements of angles, energies, and coincidences, turning invisible nuclear events into data that can be matched with theory. The applications are wide-ranging. In energy, fission occurs when a heavy nucleus like uranium-235 splits into lighter fragments, releasing enormous energy along with extra neutrons. If managed carefully, these neutrons sustain a chain reaction, as in a nuclear reactor. In fusion, light nuclei such as hydrogen isotopes merge into helium, releasing even greater amounts of energy. Fusion powers the sun, where immense pressure and temperature allow reactions to continue for billions of years. On Earth, research into magnetic confinement and laser-driven methods aims to replicate these conditions. Both fission and fusion demonstrate the central role of nuclear binding energy in powering stars and, potentially, human civilization. In medicine, nuclear physics provides tools for both diagnosis and treatment. Positron emission tomography uses isotopes that emit positrons, which annihilate with electrons to produce photon pairs detected by scanners. This creates detailed images of metabolic processes inside the body. In cancer therapy, isotopes are chosen for their ability to deliver targeted radiation to tumors, sparing surrounding tissue. Understanding how radiation interacts with matter, ionization, excitation, and energy deposition links nuclear physics directly to clinical outcomes and patient safety. In geology and archaeology, radiometric dating relies on well-known half-lives. By comparing parent and daughter isotopes in minerals, scientists can determine the ages of rocks, meteorites, and even ancient artifacts. At shorter timescales, isotopes formed by cosmic rays provide clocks for ice cores and groundwater. Even works of art are studied with nuclear techniques, using neutron activation or ion beams to analyze pigments without damage. In astrophysics, nuclear physics explains stellar life cycles and the origin of the elements. Fusion chains in stars build heavier nuclei from hydrogen, balancing gravity with radiation pressure. When stars collapse and explode as supernova, they create extreme conditions for nucleosynthesis, forming elements heavier than iron through neutron capture. The abundances of elements across the universe carry the imprint of these nuclear processes. Theoretical nuclear physics spans a hierarchy. At the most fundamental level, quantum chromodynamics describes quark and gluon dynamics. Directly solving it for nuclei is nearly impossible, so physicists use effective theories and potentials to describe nucleon-nucleon interactions. Many-body methods, mean field, density functional, or coupled cluster, predict nuclear energies, shapes, and transitions. These models are tested against spectroscopy, electromagnetic properties, and decay measurements. Exotic nuclei with extreme neutron-to-proton ratios stretch these models further. Some show halo structures with diffuse neutron clouds, others exhibit unexpected shell patterns. These studies not only expand theory, but also inform astrophysics and refine our knowledge of nuclear limits. Precision experiments also use nuclei to probe deeper physics. Searches for electric dipole moments could reveal why matter dominates over antimatter. Studies of rare double beta decay may show whether neutrinos are their own antiparticles. These delicate measurements push technology to its limits, using rare isotopes and ultrasensitive detectors. Because radiation can harm living tissue, nuclear science includes a rigorous safety culture. Dosimetry measures absorbed doses, radiobiology explains cellular effects, and shielding principles ensure safe use in reactors, hospitals, and research labs. Beneficial applications depend on this discipline, ensuring that nuclear physics remains a force for progress without unnecessary risk. At its core, nuclear physics illustrates emergence. Although nucleons are made of quarks, within the nucleus they behave as effective particles governed by residual forces. From these interactions emerge shells, vibrations, rotations, and collective modes. Different levels of description coexist, each valid in its context. The discipline continues to advance through new accelerators, powerful detectors, and improved theory. Machine learning and high-performance computing are helping reveal patterns in complex data, but physical insight remains essential. Nuclear physics, then, is not a narrow specialty, but a broad framework for understanding matter at one of its most consequential scales. It explains why elements sit in their places on the periodic table, why stars shine, why some isotopes endure and others vanish quickly, and how rearrangements of nucleons illuminate medical scanners or power entire cities. The energies it reveals are enormous compared with chemistry, but its subtleties, rare decays, delicate symmetry violations, faint neutrino signals, are just as important. Though the nucleus is unimaginably small, it shapes our world and the cosmos. The atoms in your body are the end products of stellar alchemy. Every breath you take carries the legacy of ancient nuclear furnaces. In this way, nuclear physics reminds us that even in the smallest places, the universe has written its grand story, and that we too are part of that unfolding script. Chapter 2. The Atom's Hidden Core. The nucleus of the atom is one of nature's most remarkable structures. It is unimaginably small compared to the full extent of the atom, yet it contains nearly all the atom's mass and defines its identity. To see this contrast clearly, imagine scaling an atom up to the size of a sports stadium. The electrons would be darting about the stands, and the nucleus would sit at the center, smaller than a single grain of rice. Despite its minuteness, the nucleus embodies the essence of the element. The number of protons within it distinguishes one kind of atom from another. Carbon is carbon because it has 6 protons in its nucleus, while oxygen has 8, uranium-92. The hidden core carries this defining charge, and it is here that nature's deepest forces are at play. Protons and neutrons, the nucleons, are not simply packed together like marbles in a jar. Instead, they form a quantum system where their positions and momenta are described by probability distributions rather than fixed orbits. At first glance, it may seem strange that the nucleus can even exist. Each proton carries a positive electrical charge, and like charges repel. The electric repulsion between protons should, in principle, blow the nucleus apart. But nature has another force to counteract this, the strong nuclear force. Unlike electromagnetism, it is powerful but short-ranged, effective only over distances of a femtometer, about 1/1,000,000th of a millimeter. Within this range, the strong force overpowers repulsion, binding protons and neutrons tightly together. Outside it, the force quickly falls to insignificance, allowing the nucleus to have a finite surface and not extend indefinitely. The nucleus also reveals the delicate balance between order and instability. For small numbers of protons and neutrons, the strong force holds them together efficiently. As nuclei grow larger, with dozens or even hundreds of nucleons, the long-range electrostatic repulsion increases, gradually straining the cohesion provided by the strong interaction. This is why there are limits to how large stable nuclei can be. Beyond a certain size, the balance tips, and nuclei become unstable, prone to decaying into smaller fragments. The chart of the nuclides, an atlas of all known nuclear species, shows regions of stability and instability, like a map of islands and oceans. Stable isotopes lie in a narrow band, while the rest, though fascinating to study, transform over time into more stable configurations. The hidden core is not a static ball. Nuclei can deform, vibrate, and rotate. They can take on spherical shapes, elongated ellipsoids, or more complex geometries, depending on the numbers of protons and neutrons they contain. These deformations reflect the interplay of shell effects and collective behaviors. The nuclear shell model, one of the central successes of mid-20th century physics, explains why certain numbers of protons or neutrons give nuclei extra stability. Just as electrons occupy shells around the nucleus, nucleons fill shells within the nucleus. Closed shells, complete sets of energy levels, produce particularly stable arrangements. These magic numbers leave their mark on the abundance of elements in nature and the structure of heavy nuclei. Yet nuclei can also exhibit collective motion. The whole assembly can oscillate or spin, producing characteristic patterns in the radiation they emit. This combination of individual and collective behavior makes the nucleus an extraordinary laboratory for studying emergent phenomena in quantum systems. To probe the hidden core, scientists use clever experiments. Because nuclei are so tiny, they cannot be imaged with light. Instead, their structure is revealed through scattering experiments in nuclear reactions. Bombarding a thin foil of atoms with high-energy particles and observing how those projectiles scatter provides clues about the size and distribution of charge inside nuclei. When neutrons, which have no charge, are used as probes, they interact only through the strong force, yielding complementary information. Sophisticated detectors record the energies and angles of scattered particles, reconstructing the hidden geometry of the nucleus from indirect traces. Over decades, these experiments have established that nuclei have densities roughly constant across the periodic table, about 100 trillion times denser than ordinary matter. They also show that the radius of a nucleus grows only slowly with mass, scaling roughly with the cube root of the number of nucleons. The hidden core is also dynamic in how it responds to energy. Exciting a nucleus with a particle or photon can lift it into a higher energy state, where it may vibrate collectively or rearrange its internal configuration. Eventually, it releases this energy by emitting a gamma ray, a photon far more energetic than visible light. The spectrum of these gamma rays provide the fingerprint of the internal levels of the nucleus, much as the lines in atomic spectra reveal the energies of electron shells. By studying these emissions, nuclear physicists chart the ladder of nuclear states and gain insight into how protons and neutrons organize themselves. Understanding the core also requires looking deeper still into the nature of protons and neutrons themselves. Each is a composite particle made of 3 quarks bound by gluons, the carriers of the strong interaction. At the scale of the nucleon, quantum chromodynamics describes how quarks and gluons interact. However, the equations are extraordinarily complex, and direct calculations for entire nuclei are only possible for the very lightest systems. For most of nuclear physics, nucleons can be treated as effective particles, their interactions captured by potentials derived from experiment and theory. This layered approach is a hallmark of physics. Different scales require different descriptions, and what emerges at one scale can be radically different from the underlying rules at another. One remarkable manifestation of this layered description is the nuclear binding energy curve. When the binding energy per nucleon is plotted against mass number, it rises rapidly for light nuclei, peaks near iron and nickel, and then gently declines for heavier systems. This curve is the foundation of both fusion and fission. Light nuclei can release energy by fusing into heavier ones up to iron, while very heavy nuclei can release energy by splitting into fragments closer to iron. The curve is not simply an abstract plot, it is a map of the energy landscape of matter, shaping the processes that power stars and human technologies alike. Within the hidden core lie subtleties that continue to intrigue scientists. For example, nuclei far from stability, those with extreme ratios of neutrons to protons, display behaviors that challenge established models. Some exhibit neutron halos, where 1 or 2 neutrons hover loosely bound at a large distance from the central cluster, giving the nucleus an unexpectedly large radius. Others show shifts in shell closures, where the magic numbers that apply near stability no longer hold. These exotic isotopes can be created in specialized facilities that accelerate stable ions, smash them into targets, and filter out the rare, short-lived products. Studying their decays and reactions helps refine theories of the strong interaction and illuminates astrophysical processes like nucleosynthesis in supernovae and neutron star mergers. Another frontier is the study of the shapes of nuclei. Certain isotopes exhibit shape coexistence, where different geometric configurations, spherical, prolate, oblate, exist at nearly the same energy. Transitions between these shapes manifest in gamma-ray spectra and reaction cross-sections. These findings show that even within the tiny confines of the nucleus, geometry and symmetry play crucial roles. The richness of nuclear shapes provides a natural laboratory for exploring symmetry breaking, collective dynamics, and the emergence of order from the complex interplay of forces. The hidden core is also the stage for subtle violations of symmetry that reach into the deepest questions of physics. For instance, measurements of nuclear decays revealed that nature distinguishes left from right, a discovery that overturned long-held assumptions about parity symmetry. Searches for electric dipole moments of nuclei probe time reversal violation, which could help explain why matter dominates over antimatter in the universe. These precision studies require extraordinary sensitivity, using carefully chosen isotopes and environments to amplify possible signals. They demonstrate how the atomic nucleus, though small, can test principles that govern the cosmos itself. The study of nuclear matter extends beyond individual nuclei. Under extreme conditions, such as in neutron stars, matter is compressed to densities where nuclei dissolve and neutrons form a degenerate quantum fluid. Laboratory experiments using heavy ion collisions aim to recreate aspects of these conditions, smashing nuclei together at high energies to form hot, dense matter for fleeting instants. By analyzing the debris, scientists extract information about the nuclear equation of state, the relationship between pressure, density, and temperature in nuclear matter. This equation of state determines the structure of neutron stars and the dynamics of their collisions, linking terrestrial experiments with cosmic phenomena observed through gravitational waves and X-ray astronomy. The hidden core is thus a meeting point of scales and disciplines. It connects the microcosm of quarks and gluons with the macrocosm of stars and galaxies. It informs technologies as practical as medical imaging and as ambitious as fusion power. It challenges theory with its richness of structures and behaviors, while offering experimentalists an endless variety of phenomena to uncover. The nucleus is both simple in its essence, a cluster of protons and neutrons, and complex in its manifestations, a quantum many-body system where emergent properties rule. To appreciate the significance of this hidden core, one must also reflect on its role in our own existence. Every atom in your body is defined by the number of protons in its nucleus. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it derives its identity from the atomic nucleus. And every one of those nuclei was forged in cosmic furnaces long before the Earth existed. The hidden core is not only the foundation of matter, but also the record of cosmic history. To understand it is to understand both the smallest and the largest scales of reality. Though invisible and beyond ordinary senses, the nucleus whispers a profound truth, that from its tiny realm flows the energy of stars, the passage of geological time, the signatures of ancient art, and the very fabric of life. And in contemplating the atom's hidden core, you glimpse the paradox of existence, that the deepest mysteries of the cosmos lie folded within the smallest spaces. Chapter 3. Forces that hold the nucleus together. The nucleus is a paradoxical object. Within a space of only a few femtometers, it holds together positively charged protons that by all expectations should repel one another with enormous force. The fact that nuclei exist at all is evidence of an additional interaction, one stronger than the repulsive push of electromagnetism, that binds protons and neutrons together into a compact system. To understand this binding is to uncover one of the central achievements of 20th century science, the identification of the fundamental forces and their role in shaping matter. The first clue that a new force must exist came from scattering experiments and the discovery of nuclear stability. Classical physics predicted that nuclei composed of several protons should not last. The Coulomb repulsion would force them apart. Yet nature contains not only hydrogen, but also helium, oxygen, iron, uranium, and hundreds of isotopes beyond. Something must counteract the electrical repulsion on distances smaller than the diameter of the nucleus. This became known as the strong nuclear force. It is not merely strong in a descriptive sense. It is, within its range, far more powerful than electromagnetism or gravity. Without it, no nucleus beyond hydrogen could persist. The strong nuclear force has peculiar characteristics. Unlike electromagnetism, which is long-ranged and diminishes gradually with distance, the nuclear force is short-ranged. It becomes dominant only when nucleons are separated by about 1 femtometer, and it fades rapidly beyond that. This explains why nuclei have well-defined surfaces and why nuclear matter does not collapse indefinitely. Within its range, however, the force is highly attractive and can overcome the repulsion of protons. Between protons and neutrons, it acts with nearly equal strength, reflecting its origin in a deeper symmetry. Early models treated this interaction as an exchange force. In 1935, Hideki Yukawa proposed that nucleons attract one another by exchanging a massive particle, later identified as the pion. The finite mass of the exchanged particle naturally explained the short range of the interaction. Heavier exchange particles correspond to shorter interaction ranges. Yukawa's theory anticipated the later development of quantum field theory, where forces are mediated by virtual particles. In modern terms, the strong force arises from the dynamics of quarks and gluons, but at the level of nucleons, it can be effectively described by meson exchange and residual interactions. Protons and neutrons are themselves bound states of quarks, held together by the fundamental strong interaction, quantum chromodynamics, or QCD. Quarks carry a type of charge called color, and gluons act as the mediators of color force. Unlike photons in electromagnetism, gluons themselves carry color, leading to the remarkable property of confinement. Quarks cannot be isolated, but are permanently bound inside nucleons. The residual effect of this binding leaks out of nucleons as the nuclear force. One might picture nucleons as neutral atoms of color, with van der Waals-like forces arising between them. Although this analogy is imperfect, it captures the idea that the nuclear force is a secondary manifestation of the fundamental interactions of quarks. The nuclear force is also nuanced in its behavior. At very short distances, less than about half a femtometer, it turns repulsive. This repulsion prevents nucleons from collapsing into a point and provides stability to dense nuclear matter. At slightly larger separations, the force becomes strongly attractive, binding nucleons into stable configurations. Beyond a few femtometers, it falls to zero. This combination of repulsion at extremely short distances and attraction at intermediate ranges explains the saturation of nuclear matter. Each nucleon interacts most strongly only with its immediate neighbors, so nuclei maintain nearly constant density across a wide range of sizes. This saturation property also explains why the binding energy per nucleon reaches a maximum near medium-mass nuclei, such as iron and nickel. In lighter nuclei, adding more nucleons increases binding per particle because each new nucleon interacts with several others. In heavier nuclei, additional nucleons experience less net binding because of surface effects and growing Coulomb repulsion. The balance between the short-range nuclear attraction and the long-range electric repulsion sets natural limits to nuclear stability. Symmetry plays a deep role in nuclear forces. Protons and neutrons are treated as two states of a single particle called the nucleon, related by isospin symmetry. This concept, introduced by Werner Heisenberg, reflects the near equality of nuclear forces between pairs of protons, pairs of neutrons, and proton-neutron pairs. Although small differences exist due to electromagnetism and quark mass differences, isospin symmetry remains a useful organizing principle. It explains patterns in nuclear spectra and reaction probabilities, and it links nuclear physics to the underlying quark model, where up and down quarks are nearly interchangeable. Beyond the strong force, two other interactions shape the nucleus. Electromagnetism repels protons, weakening stability as charge increases. This is why the valley of stability bends toward higher neutron numbers in heavy nuclei. Additional neutrons help dilute the repulsion by contributing strong force attraction without adding charge. The weak interaction, though much less influential in binding, governs certain nuclear transformations. It allows neutrons to convert into protons and vice versa, enabling beta decay and driving processes in stellar nucleosynthesis. Gravity, by comparison, is negligible at nuclear scales, though it dominates at cosmic scales when vast numbers of nucleons are gathered in stars and neutron stars. The intricate balance of these forces becomes visible in nuclear reactions. When a neutron approaches a heavy nucleus like uranium, it can be absorbed, creating an unstable configuration that splits apart in fission. Here, the competition between strong attraction and Coulomb repulsion tips toward separation. In fusion, by contrast, light nuclei such as hydrogen isotopes must first overcome Coulomb repulsion. Once they are close enough, the strong force takes over and binds them together, releasing energy. Both processes exemplify how the interplay of fundamental forces dictates nuclear dynamics and powers both stars and reactors. Experimental evidence for nuclear forces comes from scattering studies, spectroscopy, and measurements of nuclear properties, such as magnetic moments and quadrupole deformations. Elastic scattering of nucleons reveals the repulsive core and attractive well of the interaction. Bound states of light nuclei, like the deuteron, provide benchmarks for theoretical models. The deuteron exists as a single bound state of a proton and neutron, with properties that reflect the tensor component of the nuclear force, a directional dependence that aligns spins and produces binding. Other systems, like diprotons or dineutrons, do not form bound states, emphasizing the subtlety of the interaction. Theories of nuclear forces have evolved from simple potential models to sophisticated effective field theories. In effective field theory, the complicated dynamics of quarks and gluons are replaced by a systematic expansion of interactions between nucleons, constrained by symmetries and experimental data. This approach provides a bridge between QCD and nuclear structure, allowing calculations of nuclei from first principles with increasing accuracy. Coupled with advances in computational power, these theories now reproduce binding energies and spectra of light and medium nuclei with remarkable fidelity, turning the study of nuclear forces into a quantitative science. Understanding nuclear forces is not only an academic pursuit, it has profound implications for astrophysics. In the cores of massive stars, the balance of nuclear forces and electromagnetism shapes the pathways of element formation. In neutron stars, matter is compressed to densities where nucleon interactions determine the equation of state, the relationship between pressure and density. This equation dictates how massive a neutron star can be before collapsing into a black hole, and it governs the dynamics of neutron star mergers observed through gravitational waves. Thus, the same forces that hold the nucleus together also sculpt the behavior of some of the universe's most extreme objects. The study of these forces also informs efforts to achieve controlled fusion on Earth. To replicate the sun's energy source, physicists must overcome Coulomb barriers and create conditions where nuclear attraction dominates. This requires understanding not only average binding energies, but also subtle details of reaction cross-sections, tunneling probabilities, and resonance structures. Each of these phenomena arises from the fundamental interplay of forces within the nucleus. Though much has been learned, mysteries remain. The precise nature of the nuclear force at high densities, its behavior in neutron-rich matter, and the connection between nucleon-level descriptions and quark-level dynamics are still active areas of research. New accelerators and detectors are probing exotic isotopes, while advanced simulations aim to derive nuclear structure directly from QCD. Each discovery refines our grasp of the forces that shape matter. At the human scale, it is easy to overlook how extraordinary this balance is. The solidity of the world, the chemistry of life, and the light of the stars all depend on the fine-tuned interplay between attraction and repulsion in the nucleus. If the strong force were slightly weaker, few elements beyond hydrogen would exist. If it were stronger, matter might collapse into dense clumps of neutrons. The world we know exists in the narrow space between, where protons and neutrons bind into diverse nuclei, yet still allow variety, complexity, and stability. In contemplating these forces, you glimpse the profound connection between the smallest and the largest. The same interactions that bind a proton to a neutron also power the stars, forge the elements, and echo in the gravitational ripples of colliding neutron stars. The forces within the nucleus are hidden from view, but they whisper across the cosmos, shaping everything from the iron in your blood to the starlight in the night sky. Chapter 4. Radioactivity, Nature's Silent Glow. The story of radioactivity is one of nature's most profound revelations. For most of human history, matter was assumed to be solid, immutable, and inert. Stones seemed to last forever. Metals held their form for centuries, and the atoms that composed them were thought to be eternal building blocks. This perception changed abruptly at the dawn of the 20th century, when researchers discovered that the atomic nucleus is not always stable but can transform spontaneously. Invisible emissions of particles and energy, constant and unstoppable, flow from unstable nuclei, giving rise to the phenomenon known as radioactivity. Though imperceptible to our senses, this silent glow permeates the world, marking the deep processes of nature that operate on timescales ranging from milliseconds to billions of years. The discovery of radioactivity was accidental. In 1896, Henri Becquerel, studying phosphorescence, found that uranium salts emitted penetrating rays that could fog photographic plates even when shielded from light. Soon after, Marie and Pierre Curie identified new radioactive elements, polonium and radium, demonstrating that this phenomenon was intrinsic to the atom itself. The implications were staggering. Atoms, once considered indivisible and eternal, could change into other atoms by emitting energy. Radioactivity revealed that the nucleus, far from being an inert anchor, is dynamic, unstable in many cases, and capable of transmuting one element into another. The underlying cause of radioactivity lies in the balance of forces within the nucleus. Protons repel one another through the Coulomb force, while the strong nuclear force binds nucleons together at short ranges. For certain combinations of protons and neutrons, this balance is precarious. The nucleus may find itself in a configuration with excess energy, and the only path to greater stability is transformation. That transformation is expressed in the emission of particles or radiation. Unlike chemical reactions, which require external triggers such as heat or catalysts, radioactive decay is spontaneous. No external cause is necessary, and no method of prediction can determine when an individual atom will decay. What can be predicted with precision is statistical behavior. Given a large collection of identical nuclei, one can define the half-life, the time required for half of them to undergo decay. Half-lives vary across an extraordinary range, from tiny fractions of a second to intervals exceeding the age of the universe. The forms of radioactive decay reflect different mechanisms by which nuclei move toward stability. In alpha decay, an unstable heavy nucleus emits a helium nucleus composed of 2 protons and 2 neutrons. This small, tightly bound particle tunnels through the energy barrier that holds it inside and escapes with significant kinetic energy. Alpha decay reduces both the mass and the charge of the nucleus, shifting it toward a lighter, more stable form. Beta decay, in contrast, involves the weak interaction, one of nature's fundamental forces. In beta-minus decay, a neutron within the nucleus converts into a proton, releasing an electron and an antineutrino. In beta-plus decay, a proton converts into a neutron, releasing a positron and a neutrino. These processes change the balance of protons and neutrons, nudging the nucleus toward the region of stability. Gamma decay, another mode, occurs when a nucleus left in an excited state after a transformation releases energy in the form of a high-energy photon. The nucleus itself does not change its composition, but it relaxes into a lower energy state. Each of these pathways represents the nucleus finding a new equilibrium, guided by the laws of quantum mechanics. What is most striking about radioactivity is its regularity. Although the precise moment of decay for a single atom is unpredictable, the behavior of large samples follows exact mathematical laws. If one begins with a gram of radium, its activity decreases over time in a way that can be described precisely, with half the atoms decaying in about 1,600 years. This combination of randomness at the level of the individual and strict lawfulness at the collective level is one of the defining features of quantum physics. It reminds us that predictability emerges from probabilities, and certainty arises from averages, even when the underlying events are inherently uncertain. The discovery of radioactive decay quickly found practical applications. One of the earliest was radiometric dating. Certain isotopes, such as uranium-238, decay through long chains of transformations into stable lead isotopes with half-lives of billions of years. By measuring the ratio of uranium to lead in rocks, geologists can determine the age of Earth's oldest minerals, establishing the antiquity of our planet at more than 4 billion years. Shorter-lived isotopes, like carbon-14, provide clocks for archaeology. Carbon-14 is continually produced in the upper atmosphere by cosmic rays interacting with nitrogen. Living organisms incorporate carbon from the atmosphere, maintaining a constant ratio of carbon-14 to carbon-12. Upon death, the intake stops and the carbon-14 decays. Measuring the remaining fraction reveals the age of once-living material up to tens of thousands of years old. These dating methods tie the silent glow of radioactivity directly to human history and the story of Earth itself. Radioactivity also illuminates the cosmos. Observations of gamma-ray emissions from space reveal the presence of freshly synthesized radioactive isotopes in supernovae, tracing the nuclear processes that create the elements. In the deep interiors of stars, chains of nuclear reactions, many of which involve unstable isotopes, forge the heavier elements that are later dispersed into space. The detection of specific decay signatures in meteorites provides evidence of nucleosynthetic events that occurred before the solar system formed. Thus, radioactive decay is not only a terrestrial phenomenon, but also a window into cosmic history. In medicine, the controlled use of radioactive isotopes has transformed diagnosis and therapy. Tracers labeled with isotopes that emit gamma rays or positrons allow physicians to image metabolic processes in living tissues. Positron emission tomography, for example, maps the uptake of glucose in the brain or tumors by detecting the annihilation photons produced when positrons meet electrons. In treatment, isotopes such as iodine-131 deliver targeted doses of radiation to specific tissues, destroying malignant cells while sparing surrounding structures. Radiation therapy exploits the ability of high-energy emissions to break molecular bonds and damage DNA, selectively killing rapidly dividing cancer cells. These applications rest on a deep understanding of nuclear decay and its biological effects. The silent glow of radioactivity also demands caution. Ionizing radiation has enough energy to strip electrons from atoms, breaking chemical bonds and damaging biological molecules. In small doses, the body can repair this damage, but high or prolonged exposures increase the risk of mutations and cancer. The legacy of nuclear accidents and weapon tests demonstrates the destructive potential of uncontrolled radiation. This dual nature, beneficial in controlled use, harmful when mismanaged, makes radioactivity both a powerful tool and a serious responsibility. Modern standards for radiation protection rely on precise dosimetry, shielding, and monitoring, all rooted in the physics of radioactive decay. At the fundamental level, radioactivity is also a window into the weak interaction and the structure of the nucleus. Beta decay, for example, revealed that nature violates parity symmetry. It distinguishes left from right. The study of decay spectra and lifetimes provides tests of conservation laws, including energy, momentum, and angular momentum. Rare processes such as double beta decay are probed for insights into the nature of neutrinos and the fundamental symmetries of matter. Radioactivity is not simply a curiosity of unstable atoms, but a laboratory for testing the deepest principles of physics. From the perspective of energy, radioactive decay releases amounts far greater than chemical reactions. An alpha particle leaves the nucleus with several million electron volts of energy, orders of magnitude more than the few electron volts typical of chemical bonds. This energy density explains why small amounts of radioactive material can produce measurable heat. The warmth of Earth's interior is maintained in part by the decay of long-lived isotopes such as uranium, thorium, and potassium. Without this constant supply of energy, plate tectonics and volcanic activity might long ago have ceased, depriving Earth of the processes that recycle elements and sustain habitability. Radioactivity is therefore not only a curiosity but also a planetary engine. The study of radioactivity continues to evolve. New isotopes are synthesized in laboratories and their decay properties mapped. These measurements expand the nuclear chart and refine models of nuclear stability. Sophisticated detectors monitor decay chains for rare events that could signal new physics. Applications extend to environmental monitoring, industrial radiography, and security screening. Everywhere the silent glow of unstable nuclei finds a role, its constancy and reliability harnessed for human knowledge and safety. Yet for all its utility, radioactivity remains a reminder of the hidden dynamism within matter. What once seemed inert is alive with transformation. Deep within minerals, in the tissues of living beings, and across the stars, nuclei quietly change, each decay a small step in the universe's unfolding story. The half-lives of isotopes weave a clock that measures time in both fleeting instants and cosmic eons. The same decay that threatens life in high doses is also the process that records Earth's history and creates images of the living brain. And there's a quiet philosophical lesson here. Stability itself is often an illusion, built upon balances that eventually shift. Even atoms, those supposed eternal foundations, carry within them the seeds of change. The silent glow of radioactivity reminds us that impermanence is woven into the fabric of existence. The elements in your body were shaped by countless decays in ancient stars. The warmth beneath your feet comes from nuclei still releasing their energy after billions of years. In the silence of night, radioactivity continues its work unseen, a reminder that transformation is the universe's most enduring truth. Chapter 5. Nuclear Fission, Splitting the Unsplittable. The discovery of nuclear fission marked one of the most transformative moments in modern science. For centuries, the atom was imagined as the ultimate unit of matter, indivisible and eternal. Even after the structure of the nucleus became clear, most physicists assumed that while unstable nuclei could decay through the quiet processes of radioactivity, a heavy nucleus could not simply split into two major fragments. That assumption ended in 1938, when Otto Hahn and Fritz Strassmann, studying neutron interactions with uranium, observed that barium, an element much lighter than uranium, appeared among the products. Their colleague Lise Meitner, working with her nephew Otto Frisch, realized that they were witnessing something extraordinary. The uranium nucleus had split apart, releasing an enormous amount of energy. The term fission, borrowed from biology, was applied to describe this division of a once-thought, unsplittable entity. The essence of nuclear fission lies in the competition between two forces, the strong nuclear force and the Coulomb repulsion. In a heavy nucleus such as uranium-235 or plutonium-239, the binding provided by the strong force is balanced precariously against the repulsion of dozens of protons. When an extra neutron enters the nucleus, it can tip the balance. The nucleus becomes distorted, elongating into a shape with two lobes. At some point, the repulsion between the protons in each lobe exceeds the attraction that still holds them together, and the nucleus divides into two fragments of intermediate mass. These fragments are highly charged and fly apart with immense kinetic energy, carrying with them most of the energy released in the process. Additional neutrons are also emitted, which can in turn trigger further fissions if they are absorbed by nearby nuclei. Thus, one fission event can cascade into many, producing a chain reaction. The energy released in fission is staggering when compared with chemical processes. A single fission of uranium-235 liberates around 200 million electron volts, whereas the combustion of a single molecule of coal or gasoline releases only a few electron volts. This factor of tens of millions reflects the difference between nuclear binding energies and chemical bond energies. At the macroscopic level, 1 kilogram of uranium fuel, if completely fissioned, would yield as much energy as thousands of tons of coal. This immense density of energy explains both the promise of nuclear reactors and the destructive power of nuclear weapons. The physics of fission is subtle. Not every isotope can undergo fission readily. Uranium-238, the most common isotope of uranium, is not easily fissioned by slow neutrons, though it can undergo fission with sufficiently fast ones. Uranium-235, by contrast, has the special property of being fissile with slow or thermal neutrons. This distinction arises from the structure of nuclear energy levels and the probabilities of neutron capture at different energies. When a thermal neutron is captured by uranium-235, the resulting uranium-236 nucleus is left in a highly excited state, above the threshold needed to split. The cross-section for this process is high, meaning the probability of fission is significant. Plutonium-239, produced artificially from uranium-238 in reactors, shares this property, making it another key fissile isotope. These details are crucial, for they determine which materials can sustain a chain reaction and which cannot. The products of fission are themselves unstable. The fragments, typically with mass numbers around 90 and 140, are far from the line of stability. They undergo a series of beta decays, transforming towards stable isotopes. These decays release additional energy in the form of electrons, gamma rays, and antineutrinos. The combination of prompt energy from the immediate fission event and delayed energy from radioactive decay contributes to the total energy output of a reactor. It also explains why spent nuclear fuel remains highly radioactive and thermally hot for long periods, requiring careful handling and storage. The chain reaction is the defining feature of nuclear fission's technological importance. When each fission produces, on average, more than one neutron that causes another fission, the process can grow exponentially. This principle underlies both the functioning of nuclear power plants and the terrifying potential of nuclear weapons. The difference lies in control. In a power reactor, the chain reaction is maintained at a steady rate, with neutron absorbers, moderators, and geometry carefully designed to balance production and loss. In a weapon, the chain reaction is allowed to proceed uncontrollably, releasing an immense burst of energy in microseconds. The same physics permits both outcomes. Human intent and engineering determine whether fission is harnessed for light or unleashed for destruction. In reactors, moderation plays a key role. Neutrons produced in fission are fast, with energies of about 2 million electron volts. To increase the probability of fission in uranium-235, these neutrons must be slowed down to thermal energies. Materials such as water, heavy water, or graphite act as moderators, scattering neutrons without capturing them, reducing their speed until they can efficiently induce fission. Control rods made of neutron-absorbing materials such as cadmium or boron are inserted into the reactor core to adjust reactivity. By raising or lowering these rods, operators regulate the chain reaction, ensuring it remains steady. The heat produced by fission is transferred to water or another coolant, generating steam to drive turbines and produce electricity. This controlled conversion of nuclear binding energy into usable power is one of the most striking achievements of applied science. The byproducts of fission, however, present challenges. The fragments include isotopes such as iodine-131, cesium-137, and strontium-90, which are highly radioactive and biologically hazardous. Their half-lives range from days to decades, meaning they persist in the environment and require long-term management. The presence of plutonium in spent fuel, with its long half-life and potential use in weapons, adds another dimension of complexity: nuclear waste management. Isolating and containing these materials over geological timescales remains one of the central concerns of nuclear technology. Solutions range from deep geological repositories to recycling strategies, but the challenge underscores the profound consequences of splitting the unsplittable. Fission also illuminates astrophysical processes. While fusion dominates in stellar interiors, fission may play a role in certain exotic environments, such as neutron star mergers. The R process, or rapid neutron capture process, responsible for creating the heaviest elements in the universe, involves nuclei so neutron-rich that they undergo fission, recycling material into lighter nuclei and shaping the abundance of elements. In this way, the same process that fuels reactors on Earth contributes to the cosmic tapestry of matter. Observations of kilonovae, brilliant explosions following neutron star collisions, show signatures of radioactive decay, some likely linked to fission recycling. The study of fission, therefore, extends from laboratory reactors to the cosmic scale. Theoretical descriptions of fission remain complex. Unlike simple radioactive decays, which can be described with quantum tunneling through well-defined barriers, fission involves the collective motion of hundreds of nucleons reshaping into two separate fragments. Models use concepts like potential energy surfaces, shell corrections, and collective dynamics to describe the path from the compact nucleus to the scission point where fragments separate. Even with modern computing power, predicting the exact distribution of fission products for a given isotope remains challenging. Yet progress continues, with microscopic approaches linking fission dynamics to fundamental nucleon interactions, narrowing the gap between phenomenology and first principles. The significance of fission extends beyond energy. Its discovery reshaped global politics, altered the course of wars, and introduced humanity to the reality that the hidden forces of the nucleus could be harnessed on scales previously unimaginable. The bombings of Hiroshima and Nagasaki demonstrated the destructive capacity of uncontrolled chain reactions, while the subsequent development of nuclear power offered a vision of nearly limitless energy. The dual nature of fission, promise and peril, has defined much of the modern age. The same process that lights homes also fuels fears, shaping policy, diplomacy, and international relations. Fission has also spurred advances in fundamental science. Research reactors provide intense sources of neutrons used to probe materials, study magnetic structures, and test new theories in condensed matter physics. The neutrons from fission are also invaluable in medicine, where neutron beams contribute to cancer therapies and radioisotope production. Thus, even apart from electricity generation, the products of fission underpin a wide range of scientific and medical endeavors. Yet beneath all the applications and implications lies a simple truth. The nucleus, once considered indivisible, can be split. This realization reshaped our understanding of matter. It revealed that stability is conditional, that even the largest nuclei can fragment when pushed beyond their limits. It showed that immense energy resides within the nucleus, waiting to be released if the right conditions are met. It reminded humanity that the building blocks of the world are not fixed but dynamic, mutable, and profoundly powerful. To reflect on fission is to contemplate both wonder and responsibility. The same process that powers stars in their death throes, that shapes the abundance of elements in the cosmos, also lies within our grasp. The same neutrons that sustain a steady flame of energy in a reactor can ignite a fireball of devastation. Nuclear fission stands as a reminder of the dual edges of knowledge, that to understand is also to wield, and to wield is to bear consequence. And perhaps the deepest lesson is this: within the silence of matter itself, within the unsplittable atom, lies both the potential for destruction and the possibility of creation. The choice of how to use that potential belongs not to nature, but to us. Chapter 6: Nuclear Fusion, Power of the Stars. Nuclear fusion is the process by which light atomic nuclei merge to form heavier nuclei, releasing extraordinary amounts of energy in the process. While fission demonstrates the instability of large nuclei and their tendency to split into smaller fragments, fusion is the complementary phenomenon. It reveals that very light nuclei can achieve greater stability by joining together. This joining lies at the heart of stellar energy production, and through it, the universe has been illuminated for billions of years. Every ray of sunlight, every gleam of starlight we see in the night sky originates in the depths of fusion reactions that have been unfolding quietly but relentlessly since the earliest days of the cosmos. The scientific foundation of fusion arises from the nuclear binding energy curve. For the lightest elements, such as hydrogen and helium, binding energy per nucleon increases sharply with mass. This means that by combining light nuclei, the resulting system achieves a lower energy state, releasing the difference as radiation and particle motion. The process is only efficient up to elements around iron and nickel, where the curve reaches its peak. Beyond this point, nuclei no longer gain stability by fusing, which explains why stellar fusion does not naturally produce elements heavier than iron in significant quantities. For those heavier nuclei, different processes, such as neutron capture and supernova, are required. Thus, the energy of stars comes predominantly from fusing the lightest and most abundant element, hydrogen. Fusion, however, faces a formidable barrier: the repulsion between positively charged protons. To bring two nuclei close enough for the strong nuclear force to act, they must overcome this Coulomb barrier. In stars, this is achieved through a combination of high temperatures, immense pressures, and the tunneling effects of quantum mechanics. At millions of degrees, the particles within stellar cores move with sufficient energy to approach one another, and although most collisions still lack the energy to surmount the barrier, quantum tunneling allows a fraction of nuclei to penetrate it. This small but crucial probability enables fusion to proceed even at conditions that would seem, from a purely classical perspective, inadequate. The quiet persistence of these improbable events fuels stars for billions of years. Different pathways of fusion dominate in stars of different sizes and ages. In stars like our Sun, the proton-proton chain is the primary mechanism. It involves a sequence of reactions where protons fuse to form deuterium, which then fuses further to produce helium, with positrons, neutrinos, and gamma rays emitted along the way. The net result is the conversion of 4 hydrogen nuclei into 1 helium nucleus, with a small loss of mass that appears as energy according to Einstein's relation. In more massive stars, the carbon-nitrogen-oxygen cycle becomes dominant. Here, hydrogen fusion proceeds with carbon, nitrogen, and oxygen nuclei acting as catalysts, cycling through different isotopes, but ultimately achieving the same transformation of hydrogen into helium. The efficiency of this cycle increases strongly with temperature, making it the main pathway in hotter, heavier stars. Regardless of the details, all stellar fusion is a manifestation of the same principle: the release of energy as light nuclei coalesce into more stable forms. The stability provided by fusion defines stellar lifetimes. For stars like the Sun, the balance between gravitational contraction and fusion energy sustains equilibrium for billions of years. If fusion were to cease, gravity would cause the star to collapse. If fusion ran too quickly, the star would expand and cool, slowing the reaction. This delicate, self-regulating balance, governed by the interplay of fundamental forces, is what allows stars to shine steadily. When hydrogen fuel is eventually exhausted in the core, stars evolve through new stages, fusing helium and heavier elements in shells, producing a layered structure that eventually culminates in either a gentle fading or a dramatic collapse, depending on mass. Thus, fusion not only powers stars but also dictates their birth, evolution, and ultimate fate. The role of fusion in the cosmos extends beyond light and heat. It is the origin of nearly all elements in the periodic table, up to iron. Helium was formed in the first minutes after the Big Bang through primordial nucleosynthesis, but everything heavier, carbon, oxygen, nitrogen, and the elements essential to life, was built in stellar interiors by successive fusion processes. The carbon in our bodies was once part of the triple alpha reaction in a dying star, where 3 helium nuclei combine to form carbon. Oxygen arose from the fusion of carbon and helium. These processes stitched together the chemical complexity that life requires, dispersing it into space through stellar winds and supernova explosions. When we breathe oxygen or metabolize carbon-based molecules, we are literally participating in the aftermath of nuclear fusion that took place long before Earth formed. On Earth, fusion has become both a dream and a challenge. The promise is nearly limitless energy, fueled by isotopes of hydrogen such as deuterium and tritium. Deuterium exists abundantly in seawater, while tritium can be bred from lithium. The energy yield of their fusion is immense, producing helium and a high-energy neutron. The difficulty lies in recreating the conditions of stellar interiors without the assistance of gravity on astronomical scales. Temperatures of hundreds of millions of degrees are required, and the plasma created under such conditions must be confined long enough for fusion to occur at a useful rate. Magnetic confinement, using devices such as tokamaks and stellarators, attempts to hold the plasma in magnetic fields shaped like donuts or twisted spirals, keeping it away from material walls. Inertial confinement, by contrast, uses powerful lasers or particle beams to compress tiny fuel pellets to extreme densities and temperatures in fleeting bursts. Both approaches strive toward the same goal: to ignite a sustained, controlled fusion burn that produces more energy than it consumes. Progress has been steady but arduous. Experiments have demonstrated fusion reactions for decades, but reaching net energy gain, where output exceeds input, has been elusive. Advances in superconducting magnets, laser technology, and plasma physics have brought the goal closer. International projects, such as the ITER reactor in France, aim to demonstrate large-scale sustained fusion within this century. Success would revolutionize energy production, offering a source with virtually no greenhouse gas emissions, minimal long-lived radioactive waste, and fuel that is abundant across the planet. The obstacles are formidable, but the potential reward is transformative. To harness the same process that powers the stars, fusion is not without hazards. The high-energy neutrons produced in deuterium-tritium reactions activate materials, creating secondary radioactive waste. The engineering challenge of managing plasma instabilities, neutron damage to reactor walls, and the continuous handling of tritium requires solutions at the frontier of technology. Yet the comparison with fission is striking. Fusion does not risk runaway chain reactions. Its fuel cannot be stockpiled into destructive weapons as easily. And the scale of available fuel, oceans of deuterium, offers a vision of energy abundance that could sustain civilizations for millennia. Fusion, if achieved, could represent not merely another energy source, but a new chapter in the relationship between humanity and nature. From a theoretical perspective, fusion illustrates the richness of quantum mechanics. The very possibility of tunneling allows nuclei to fuse at temperatures lower than would be classically required. This small probability, repeated countless times, lights the stars. It also underlines the importance of collective behavior. While individual events are rare, the immense number of particles in a stellar core ensures that enough fusion occurs to balance gravity. The Sun alone fuses about 600 million tons of hydrogen into helium every second, yet from our vantage point it seems steady and serene. This quiet persistence is the mark of fusion's power. Fusion also serves as a laboratory for understanding matter under extreme conditions. The plasmas involved are unlike anything on Earth, where particles are stripped of electrons and interact through long-range electromagnetic forces. The instabilities, turbulence, and magnetic reconnections in these plasmas echo phenomena observed in astrophysical environments. By studying fusion on Earth, physicists gain insight not only into energy generation, but also into the dynamics of cosmic plasmas, from solar flares to accretion disks around black holes. Thus, the pursuit of fusion merges fundamental science with practical ambition, intertwining the study of the universe with the needs of civilization. The significance of fusion cannot be overstated. Without it, the universe would be dark and lifeless. It is the engine behind the cosmic cycle of matter and energy, the source of the elements that compose planets and living beings. It is also a potential solution to the challenges humanity faces in sustaining its technological society without exhausting the planet's resources. Yet fusion also conveys a more profound lesson. It shows that from improbable beginnings, particles overcoming barriers they cannot surmount in classical physics, emerges the steady brilliance of stars. It reminds us that great transformations can arise from rare possibilities, amplified over time and number. In contemplating nuclear fusion, one glimpses both our past and our future. We are made of its ashes, shaped by its processes, dependent on its energy. The light we see when we look up at night is the signature of fusion reaching across space and time. And perhaps, if our technology succeeds, fusion will one day glow not only in the heavens, but also in reactors here on Earth, providing energy as constant as the stars themselves. The lesson is humbling, that within the smallest collisions of particles lies the power to light worlds and to shape existence itself. Chapter 7. The Neutron's Strange Role. Among the building blocks of the atomic nucleus, the neutron occupies a peculiar and essential place. It is electrically neutral, lacking the positive charge of the proton and the negative charge of the electron. At first glance, neutrality might seem like a trivial feature, but in nuclear physics, it is a defining characteristic that enables the very existence of complex matter. Without neutrons, nuclei heavier than hydrogen could scarcely form. With too many neutrons, nuclei become unstable and prone to decay. The neutron is both a stabilizer and a destabilizer, both a participant in binding and a driver of transformation. Its strange role reveals itself in contexts ranging from the interior of atomic nuclei to the cores of stars, from the quiet glow of radioactivity to the violent collisions of neutron stars across the cosmos. The neutron itself is a composite particle. Like the proton, it is made of 3 quarks bound together by gluons in the framework of quantum chromodynamics. Specifically, the neutron contains 2 down quarks and 1 up quark, giving it a slightly greater mass than the proton. This mass difference is small in absolute terms but crucial in its consequences. A free neutron, unbound from any nucleus, is unstable. After about 15 minutes, it undergoes beta decay, transforming into a proton, an electron, and an antineutrino. This instability explains why hydrogen, with a single proton and no neutrons, is the simplest and most abundant element in the universe. If neutrons were exactly stable in isolation, matter might look entirely different, perhaps dominated by neutron-rich assemblies rather than the diversity of elements we know. Inside nuclei, however, neutrons achieve stability through binding. When coupled with protons, they contribute to the strong nuclear force that holds the nucleus together without adding to the electrostatic repulsion that protons exert on one another. In this way, neutrons act as a kind of nuclear glue. Helium, for example, has 2 protons and 2 neutrons. If it contained only protons, the repulsion between charges would make the nucleus fly apart. The neutrons supply the necessary attraction to counterbalance the repulsion, creating one of the most stable nuclei in nature. As elements grow heavier, the need for neutrons increases. For carbon, with 6 protons, an equal number of neutrons suffices. For lead, with 82 protons, stability requires 126 neutrons. This growing neutron-to-proton ratio compensates for the increasing Coulomb repulsion among protons. The neutron thus dictates the very pattern of stability across the periodic table. Yet neutrons are also the agents of instability. Too few neutrons, and a nucleus undergoes positron emission or electron capture, transforming a proton into a neutron to restore balance. Too many neutrons, and the nucleus undergoes beta- decay, converting a neutron into a proton. The neutron's ability to shift identity through the weak interaction is what allows the nuclear landscape to maintain its narrow valley of stability. It also underpins nucleosynthesis in stars, where neutron-rich isotopes evolve towards stable configurations through chains of decays. The neutron, in this sense, is the pivot of nuclear transformation, enabling matter to move between different states of balance. The strange role of the neutron extends to nuclear reactions. Because it carries no charge, the neutron does not experience Coulomb repulsion when approaching a nucleus. Unlike protons or alpha particles, it can penetrate directly into nuclear matter, even at very low energies. This makes neutrons uniquely effective as projectiles in nuclear experiments and applications. It was precisely this property that enabled the discovery of nuclear fission. When uranium was bombarded with neutrons, the incoming particles slipped past the Coulomb barrier and triggered splitting. The capacity of neutrons to enter nuclei easily also explains their central role in chain reactions. Each fission event releases additional neutrons, which can propagate the process without requiring external acceleration. The neutron is the enabler of self-sustaining nuclear reactions, whether in the steady environment of a power reactor or the uncontrolled blast of a weapon. The neutron's neutrality also makes it a subtle probe of matter. Neutron scattering experiments conducted at research reactors and spallation sources allow scientists to study the structure of solids, liquids, and biological systems. Because neutrons interact with nuclei rather than electron clouds, they provide complementary information to X-ray diffraction, revealing atomic positions, magnetic arrangements, and molecular dynamics. These techniques rely on the fact that while neutrons are neutral overall, they carry a magnetic moment due to their internal quark structure. This moment interacts with magnetic fields inside materials, enabling the study of magnetism at the atomic scale. Thus, the neutron's strange role extends beyond the nucleus, offering insight into condensed matter, chemistry, and biology. In astrophysics, neutrons play roles even more extraordinary. Within stars, neutron production is central to the synthesis of elements heavier than iron. During the S process, or slow neutron capture process, nuclei gradually absorb neutrons and undergo beta decays, building heavier elements over long stellar lifetimes. In the R process, or rapid neutron capture process, which occurs in supernovae or neutron star mergers, nuclei are bombarded with torrents of neutrons, producing exotic isotopes that later decay into stable heavy elements. The gold, platinum, and uranium on Earth owe their existence to these neutron-driven processes in cosmic cataclysms. In this sense, neutrons are not only glue within nuclei, but also the architects of the universe's chemical complexity. Neutrons also define the extreme state of matter in neutron stars. When massive stars exhaust their fuel and collapse, protons and electrons are squeezed together, forming neutrons through inverse beta decay. The result is an object composed almost entirely of neutrons, supported against further collapse by the quantum pressure arising from the Pauli exclusion principle. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers across, reaching densities unimaginable on Earth. In these environments, neutrons are no longer just constituents of nuclei, but the very fabric of matter. The behavior of neutrons under such conditions, whether they form superfluid phases, whether exotic particles appear, remains a subject of intense study, linking nuclear physics to astrophysics and gravitational wave astronomy. The neutron's instability as a free particle is itself a continuing puzzle. Measuring the neutron lifetime with high precision has proven difficult, with different experimental methods producing slightly different values. The discrepancy, though small, may hint at unknown physics, perhaps involving new particles or interactions. If the neutron decays in rare ways beyond the standard model, it could provide clues to the asymmetry between matter and antimatter in the universe. Thus, even a humble measurement like the lifetime of the neutron carries cosmological significance. In practical terms, neutrons are indispensable tools. In medicine, neutron irradiation is explored as a cancer therapy, taking advantage of the fact that certain tumors absorb boron compounds, which then undergo reactions when struck by neutrons, delivering lethal doses of radiation to cancer cells while sparing surrounding tissue. In industry, neutron radiography provides imaging methods that can reveal details invisible to X-rays, such as light elements embedded within metals. In national security, neutron detection is a cornerstone of monitoring for illicit nuclear materials, since certain isotopes emit neutrons or can be induced to do so under interrogation. Each of these applications relies on the unique properties of the neutron: neutrality, penetrability, and distinctive nuclear interactions. Despite its utility, the neutron also carries challenges. Because it has no charge, it cannot be confined easily by electric fields, making its control more difficult than that of charged particles. Free neutrons are unstable, so neutron sources must be continually replenished, whether by reactors, accelerators, or spallation facilities. The very penetrability that makes neutrons effective probes also makes them hazardous, as they can pass deeply into biological tissue and deposit energy indirectly, leading to cellular damage. Neutron protection requires specialized shielding materials, often rich in hydrogen, to slow and capture them. In this way, the neutron embodies both opportunity and risk, its strange role demanding careful respect. In reflecting on the neutron, one cannot help but be struck by its duality. It is at once fragile and powerful, unstable and indispensable, a particle that decays in minutes when free, yet forms the core of stars that last for billions of years. It defines the balance of stability in nuclei, shapes the elements forged in cosmic furnaces, and governs the behavior of matter at its densest extremes. The neutron is a reminder that neutrality is not emptiness but potential, that silence can conceal strength. In the quiet neutrality of the neutron lies the architecture of the universe and the possibility of worlds like our own. Chapter 8: How Nuclear Physics Shapes the Universe. To understand the universe at large scales, its stars, galaxies, and chemical complexity, one must also look inward to the processes that occur at nuclear scales. The physics of the atomic nucleus, seemingly confined to spaces far smaller than atoms themselves, has cosmic consequences that extend across billions of light years. Nuclear physics explains why the sun shines, how the elements formed, why planets possess internal heat, and even why life itself could emerge. From the earliest seconds of the universe to the distant future of stars, the behavior of protons and neutrons, and the forces that bind and transform them, has determined the unfolding of cosmic history. The influence of nuclear physics begins in the first minutes after the Big Bang. During the earliest fraction of a second, the universe was too hot and dense for stable nuclei to exist. Quarks and gluons formed a plasma, only later cooling enough to allow the first protons and neutrons to appear. As expansion continued and temperatures fell, these nucleons combined to form the first light nuclei. In a period known as Big Bang nucleosynthesis, hydrogen, helium, and traces of lithium and beryllium were created. The relative abundances observed today, about 3/4 hydrogen and 1/4 helium by mass, are a direct imprint of nuclear reaction rates during those brief moments. The precision with which theory and observation agree is one of the triumphs of modern cosmology, demonstrating how nuclear processes on subatomic scales set the chemical baseline of the entire cosmos. From that starting point, nuclear fusion within stars became the engine that shaped subsequent evolution. In stellar cores, hydrogen nuclei are fused into helium, releasing energy that counteracts gravitational collapse. This nuclear burning defines the main sequence of stellar lifetimes, determining whether a star will shine for billions of years like the Sun or burn more quickly as a massive, short-lived giant. The proton-proton chain in stars like our Sun and the carbon-nitrogen-oxygen cycle in more massive stars are nuclear processes that sustain the radiation we observe as starlight. Without them, stars would collapse in darkness and the universe would remain a cold, lifeless expanse. As stars exhaust their hydrogen, nuclear physics dictates their later stages. Helium fusion forms carbon and oxygen, then heavier elements through successive burning stages in massive stars. Each stage requires higher temperatures and pressures, achievable only in stars of sufficient mass. This chain of nuclear reactions explains the abundance pattern of elements, with peaks at certain atomic numbers corresponding to nuclei of particular stability. The triple alpha process, in which 3 helium nuclei combine to form carbon, is especially significant. The energy levels of carbon-12 allow this process to occur with surprising efficiency, ensuring that carbon, essential to life, is produced in large quantities. The fact that nuclear structure aligns so precisely with the needs of stellar synthesis has long been noted as a remarkable feature of nature's design, one that allowed life-friendly chemistry to emerge. Supernovae revealed the most spectacular role of nuclear physics in shaping the cosmos. When massive stars collapse, nuclear reactions proceed under extreme conditions. Explosive nucleosynthesis occurs, forging elements heavier than iron that cannot be produced in ordinary stellar burning because fusion beyond iron consumes energy rather than releasing it. Rapid neutron capture, the R process, floods nuclei with neutrons, driving them to extreme neutron-rich states that later decay into stable heavy elements like gold, platinum, and uranium. The universe's most precious materials, those that underpin advanced technologies and human culture, are products of nuclear reactions in the death throes of massive stars. The light curves and spectra of supernova bear the unmistakable signatures of radioactive decay, as isotopes like nickel-56 and cobalt-56 release energy over weeks and months, powering the fading brilliance of the explosion. In this way, nuclear physics determines not only what elements exist, but also how the cosmos shines in its most dramatic events. Nuclear reactions also shape the remnants of stellar evolution. White dwarfs, the end state of medium stars, are stabilized against collapse by electron degeneracy, but their cooling is influenced by residual nuclear burning and radioactive decay. In binary systems, runaway nuclear fusion on the surface of white dwarfs can trigger novae visible across galaxies. For neutron stars formed from the collapse of massive cores, nuclear matter itself is transformed into a dense sea of neutrons. Here, the nuclear equation of state, the relationship between pressure and density, dictates the size, mass limit, and behavior of these compact stars. Gravitational wave detections of neutron star mergers, accompanied by electromagnetic signals, provide direct evidence of nuclear processes operating under extreme densities. The kilonovae associated with such mergers glow with the light of newly synthesized heavy elements, revealing that the universe's chemical inventory is continually replenished by these cosmic collisions. Even on planetary scales, nuclear physics leaves its mark. The heat within Earth, which drives mantle convection, volcanism, and plate tectonics, is partly sustained by the radioactive decay of isotopes such as uranium-238, thorium-232, and potassium-40. Without this nuclear heat, Earth might have cooled into a geologically dead world long ago. Like the Moon, the churning of Earth's interior not only reshaped continents and mountains, but also maintained the magnetic field that shields the planet from cosmic radiation. Thus, radioactive decay, a microscopic nuclear process, has contributed to the long-term habitability of our planet. In other planets and moons, variations in radioactive inventories influence geological activity and even the potential for subsurface oceans, as in the case of some icy moons warmed by both tidal forces and nuclear heating. Cosmic rays provide another avenue through which nuclear physics shapes the universe. High-energy particles accelerated by supernova shocks or active galactic nuclei strike interstellar matter, producing showers of secondary particles and new isotopes. These interactions explain the presence of certain light elements, like lithium, beryllium, and boron, which are not officially made in stellar interiors. In Earth's atmosphere, cosmic rays create carbon-14, the isotope that underpins radiocarbon dating. Each cosmic ray interaction is a miniature nuclear reaction, shaping not only cosmic abundances, but also the tools we use to trace history on Earth. At the largest scales, nuclear physics influences cosmology itself. The amount of helium created in the Big Bang serves as a sensitive probe of the density of baryons in the early universe. The behavior of nuclear matter in neutron stars affects gravitational wave signals used to test general relativity. The properties of neutrinos, emitted in enormous numbers in nuclear reactions, influence the evolution of cosmic structure. Neutrino backgrounds, relics of both the Big Bang and countless stellar processes, permeate the universe. Their existence ties nuclear transformations to the overall shape and fate of the cosmos. In this way, the physics of the nucleus, confined in laboratories, becomes a cornerstone of our understanding of cosmology. Humanity's grasp of nuclear physics has also expanded our ability to observe the universe. Neutrino detectors capture signals from the nuclear reactions powering the sun, providing direct evidence of fusion processes. Observatories that monitor gamma rays detect the decay of freshly synthesized isotopes in distant supernovae. Experiments on Earth that measure cross-sections of nuclear reactions feed into stellar models, refining predictions of star lifetimes and abundances. Thus, the universe is not only shaped by nuclear physics, but also revealed by it, as our tools for understanding rely on the signatures of nuclear processes written across the cosmos. One of the most remarkable aspects of nuclear physics is its consistency across scales. The same principles that explain the binding of a proton and neutron into deuterium also determine the evolution of galaxies. The saturation of nuclear forces explains the stability of elements, which in turn explains the distribution of matter in stars and planets. The probabilistic nature of decay governs clocks that date human artifacts and also drives the light curves of stellar explosions. Everywhere one looks, from the smallest nuclei in laboratories to the largest stellar cataclysms, the rules of nuclear physics operate without exception. And yet, there is a humbling aspect to this universality. The cosmos, with its grandeur of galaxies and nebulae, is ultimately shaped by the behavior of particles smaller than the eye can see. The existence of life, the possibility of planets with water, and the persistence of stars for billions of years all depend on the precise values of nuclear masses, lifetimes, and reaction rates. A small change in the binding energy of deuterium or in the properties of the neutron would alter the balance of nucleosynthesis, perhaps leaving the universe barren of the elements we need. In this sense, nuclear physics is not only the science of the small, but also the science of everything. For it bridges the gap between quarks and consciousness, between the heart of atoms and the fabric of galaxies. When you gaze at the stars, you are seeing the product of nuclear transformations stretched across time and space. The warmth of the sun on your skin, the oxygen in your lungs, the iron in your blood, and the gold on a ring are all the outcomes of processes that occur in the nucleus. Nuclear physics has shaped the universe not through rare miracles, but through constant, quiet laws operating ceaselessly for billions of years. And perhaps the deepest reflection is this: the light of the universe is not only a cosmic phenomenon, but also a message from the nucleus itself, whispering that the smallest scales of reality hold the power to sculpt the greatest wonders of existence. Chapter 9. Everyday Life and Nuclear Science. When people hear the term nuclear science, they often imagine vast reactors, experimental laboratories, or perhaps the dramatic mushroom clouds of weapons testing. Yet nuclear physics is not confined to distant power plants or moments of history. It permeates daily life in ways most of us seldom recognize. The nucleus, with its subtle transformations and hidden forces, is woven into the technologies we use, the medical treatments we rely on, and even the clocks that measure our days. Though it operates at a scale far beyond our senses, nuclear science shapes the practical texture of existence in quiet, constant ways. The most obvious influence appears in the generation of electricity. Nuclear power plants provide a significant portion of the world's energy supply, offering a low-carbon alternative to fossil fuels. Inside these plants, controlled fission reactions release heat, which is transferred to water, producing steam that drives turbines. This process is not abstract physics. It becomes the electricity that lights homes, powers hospitals, and sustains industries. Beyond reactors, nuclear principles influence energy in more subtle ways. The very stability of Earth's internal heat, which drives plate tectonics and volcanic activity, relies on the natural radioactive decay of long-lived isotopes within the planet's crust. The landscape of continents, the renewal of soils, and even the long-term climate stability that has allowed human civilizations to flourish are partly products of nuclear processes deep beneath our feet. Nuclear science is also deeply embedded in medicine, where it has revolutionized both diagnosis and treatment. Positron emission tomography, or PET scanning, depends on the controlled introduction of radioactive tracers into the body. These tracers emit positrons that annihilate with electrons, producing photons detected by sensors that reconstruct images of metabolic activity. PET scans reveal how the brain consumes glucose, how tumors grow, and how organs function at a level inaccessible to conventional imaging. Other techniques, such as single-photon emission computed tomography, exploit gamma-emitting isotopes to provide functional images of blood flow or bone growth. These methods rely on precise knowledge of half-lives, decay pathways, and radiation energies, all grounded in nuclear physics. The images they provide are not mere pictures. They are windows into the invisible processes of life. Therapeutically, nuclear science has provided tools for combating disease. Radioisotopes, such as iodine-131, target the thyroid, treating hyperthyroidism and thyroid cancer with remarkable specificity. In radiotherapy, beams of gamma rays, X-rays, or accelerated particles deposit energy in tumors, damaging DNA and selectively killing malignant cells. Advanced techniques employ isotopes that deliver radiation over very short ranges, minimizing collateral damage to healthy tissue. Neutron capture therapy, for example, takes advantage of boron compounds that accumulate in tumors. When struck by neutrons, the boron undergoes a reaction that releases highly localized energy, destroying cancer cells from within. Each of these treatments arises from a profound understanding of nuclear interactions, translated into medical practice to save lives. Outside hospitals, nuclear techniques safeguard public health and safety in less visible ways. Food irradiation uses gamma rays to eliminate pathogens and pests, extending shelf life and reducing the risk of foodborne illness. Traces of radioactive isotopes are used to study how nutrients move through crops, optimizing fertilizers and improving yields. In water management, isotopes track groundwater flow, revealing how aquifers recharge and how pollution spreads. These applications may seem far from everyday concerns, but they directly influence the safety of the food we eat and the water we drink. Nuclear science also plays a crucial role in technology and industry. Non-destructive testing methods use gamma rays or neutrons to inspect materials for hidden flaws. Aircraft components, pipelines, and welds are examined with nuclear techniques to ensure safety and reliability without damaging the materials. Radiography can reveal cracks or weaknesses invisible to the naked eye, preventing accidents before they occur. In oil exploration, neutron logging tools probe the composition of rock layers, guiding drilling decisions. In manufacturing, nuclear gauges measure thickness, density, or moisture content with unparalleled precision. Each of these uses represents nuclear science translated into practical assurance, woven into the infrastructure of modern life. Another remarkable application lies in timekeeping. Atomic clocks, the most precise instruments ever built, rely on transitions in atomic nuclei and electrons. While the best-known standards use electron transitions in cesium atoms, new generations of clocks explore transitions in nuclear states themselves, offering even greater stability. These clocks define the second, synchronize global positioning systems, and regulate communications networks. The accuracy of GPS navigation, the ability to locate oneself within meters anywhere on Earth, depends on corrections measured in billionths of a second. Thus, nuclear science not only explains the distant stars but also tells us where we are on our own planet. In the realm of art and history, nuclear techniques offer tools for preservation and discovery. Radiocarbon dating, based on the decay of carbon-14, allows archaeologists to determine the age of organic artifacts. Accelerator mass spectrometry, a method rooted in nuclear physics, measures isotopic ratios with extraordinary sensitivity, revealing the chronology of human cultures and natural events. Neutron activation analysis can identify the elemental composition of pigments in paintings without damaging them, helping art historians authenticate works and trace the sources of materials. These quiet contributions of nuclear science deepen our understanding of culture and history, allowing us to glimpse lives and stories long past. The presence of nuclear processes in daily life also extends to natural radiation. We are constantly bathed in a background of cosmic rays, terrestrial isotopes, and even potassium-40 within our own bodies. This radiation is usually harmless, but it reminds us that the nuclear world is not confined to laboratories. It is an intrinsic part of existence. From the radon seeping out of rocks to the cosmic muons that streak through buildings, nuclear phenomena are ever present. Radiation detectors, employed in medicine, research, and security, make this hidden world visible, providing reassurance and protection where needed. In security and defense, nuclear science is a double-edged sword. On one hand, it provides methods to detect illicit materials, monitor treaty compliance, and prevent proliferation. Sophisticated sensors identify the unique signatures of radioactive isotopes, guarding against smuggling and terrorism. On the other hand, the destructive power of nuclear weapons remains a sobering reminder of how the same knowledge that sustains daily life can also imperil it. The contrast is stark. The same neutron that triggers a fission chain reaction in a reactor also drives the uncontrolled explosion of a weapon. This duality underscores the ethical weight carried by nuclear science in modern society. One might imagine that nuclear science is far removed from ordinary individuals, but it shapes countless routines. The electricity charging a phone may come from a reactor. The medical scan that diagnoses disease relies on radioactive tracers. The airplane one boards has components inspected by nuclear radiography. The GPS guiding a car rests on nuclear-defined time. Even the fertilizers nourishing crops are optimized through isotopic tracing. Nuclear physics, though invisible, is as present in the everyday as electricity or chemistry. Its impact is quiet, often unnoticed, yet fundamental. The pervasiveness of nuclear science raises questions of perception and trust. Radiation, though natural and ubiquitous, inspires fear, often associated with accidents or weapons. Yet our daily exposure to radiation from rocks, air, and the cosmos is part of life, just as much as sunlight or magnetism. Education and transparency are vital, helping people understand both the risks and the benefits of nuclear science. By seeing radiation not only as danger but also as a source of knowledge and healing, society can embrace the strange, silent role it plays in modern existence. Looking to the future, nuclear science may become even more entwined with daily life. Advances in fusion research, if successful, could provide abundant energy with minimal waste. Portable nuclear technologies may power remote areas or support space exploration. Medical isotopes produced with next-generation reactors and accelerators may allow even more precise targeting of disease. Nuclear forensic techniques will continue to safeguard security in an interconnected world. As each of these advances develops, the hidden processes of the nucleus will move ever closer to the center of human experience. And perhaps the most humbling realization is that nuclear science is not an artificial imposition on life, but a recognition of what has always been there. The atoms in our bodies contain nuclei born in stars. The heat of Earth arises from isotopes that have glowed silently for billions of years. The cosmic rays that flicker through us link us to distant galaxies. In studying and applying nuclear science, humanity has simply learned to listen to the quiet workings of the universe, translating them into energy, medicine, technology, and knowledge. In reflecting on this, one sees that the extraordinary is embedded in the ordinary. Nuclear physics does not only belong to distant stars or rare experiments. It lives in every breath, every heartbeat, every technological moment of modern life. The nucleus, invisible and silent, holds within it both the memory of the cosmos and the promise of the future. And in that silence lies a profound truth, that the everyday world, so familiar and ordinary, is sustained and enriched by processes unfolding far beyond our senses, binding us always to the deep story of the universe. Chapter 10. The Future of Nuclear Power and Discovery. The history of nuclear science has always carried a dual quality. It has provided humanity with extraordinary opportunities for energy and knowledge, while also confronting society with profound challenges. As we look forward, the trajectory of nuclear power and discovery seems poised to remain central in addressing the demands of a growing population, the urgency of climate change, and the quest to understand the deepest structures of matter. The nucleus, that tiny domain of protons and neutrons, continues to reveal new possibilities, not only for energy production, but also for scientific exploration and human survival in the long run. The question is no longer whether nuclear science will shape the future, but how and in what form. Nuclear fission will remain a cornerstone of this future, though it is undergoing reinvention. Traditional large-scale reactors have demonstrated that nuclear power can provide vast quantities of electricity with very low carbon emissions. Yet they also highlight the challenges: high capital costs, the long lifetimes of radioactive waste, and the societal unease tied to memories of accidents and the specter of weapons. To address these issues, new generations of reactors are being developed, often referred to as Generation 4 systems. These designs emphasize safety, efficiency, and sustainability. Some are cooled by gases or molten salts rather than water, operating at higher temperatures that improve efficiency and allow for industrial applications beyond electricity, such as hydrogen production. Others aim to close the fuel cycle, using fast neutrons to fission not only uranium-235 and plutonium-239, but also transuranic elements, reducing the long-term radiotoxicity of waste. These systems represent an effort to use nuclear resources more fully and to diminish the burdens passed to future generations. Parallel to these large designs, a different movement has emerged in the form of small modular reactors. Instead of gigawatt-scale plants, these compact units produce tens to hundreds of megawatts. Their modularity allows them to be built in factories, transported to sites, and scaled as needed. They offer potential advantages in cost, deployment speed, and flexibility, making them suitable for regions without large centralized grids. Their inherent safety features, often relying on passive cooling and simple geometries, reduce the risk of accidents. For remote communities, islands, or industrial facilities, small modular reactors may provide stable, carbon-free energy where other options are limited. This shift toward smaller, more adaptable systems illustrates how nuclear power is evolving to meet varied needs in a changing world. At the frontier lies nuclear fusion, the long-sought counterpart to fission. As discussed earlier, fusion promises energy of unprecedented abundance, fueled by isotopes of hydrogen that are widely available. While experimental progress has been slower than early optimism suggested, recent advances in superconducting magnets, laser confinement, and plasma physics have brought the dream closer to realization. Projects like ITER in France and private initiatives across the globe are pushing the boundaries of what is possible. Achieving a net energy gain from fusion more energy out than in, would mark a turning point in energy history. Fusion carries immense appeal. It produces no greenhouse gases, yields only short-lived radioactive byproducts, and cannot run away like a chain reaction. If realized, fusion power plants could operate continuously, providing baseload energy without the volatility of renewables or the carbon burden of fossil fuels. While formidable engineering challenges remain, the pursuit of fusion reflects humanity's ambition to capture the same process that powers the stars. Beyond power production, the future of nuclear discovery encompasses new ways of probing matter and the universe. High-intensity accelerators and advanced reactors generate beams of exotic isotopes, allowing physicists to explore nuclei at the edges of stability. These experiments shed light on how elements are formed in astrophysical environments, refining models of stellar nucleosynthesis and neutron star mergers. They also test the limits of nuclear theory, bridging the gap between quantum chromodynamics and the complex behaviors of many-body nuclear systems. Precision measurements of rare decays, such as neutrinoless double beta decay, may reveal whether neutrinos are their own antiparticles and why matter dominates over antimatter. Searches for electric dipole moments in nuclei probe violations of fundamental symmetries, offering clues to physics beyond the standard model. In these pursuits, the atomic nucleus becomes a laboratory for questions as vast as the fate of the universe. Nuclear science also points outward toward space exploration. Powering spacecraft beyond the reach of solar panels has long depended on radioisotope thermoelectric generators, which convert the heat from natural decay into electricity. Future missions may use compact fission reactors to supply power for bases on the Moon or Mars, enabling human presence far from Earth. Fusion, if achieved, could revolutionize propulsion, allowing spacecraft to reach outer planets and even interstellar space with unprecedented speed. Nuclear physics also provides tools for studying planetary surfaces, as neutron and gamma-ray spectrometers reveal the composition of rocks and soils from orbit. In this way, nuclear science is not only about energy, but also about expanding humanity's reach into the cosmos. The societal dimension of nuclear power cannot be ignored in envisioning the future. Public perception, regulation, and geopolitics will determine whether advanced reactors and fusion plants are widely adopted. Nuclear accidents in the past, though rare, have left deep impressions that continue to shape public attitudes. Addressing these fears requires not only technological improvements, but also transparency, education, and trust. International cooperation is also essential, since nuclear materials and technologies cross borders. Safeguards and monitoring systems ensure that nuclear energy remains peaceful, preventing diversion to weapons. The future of nuclear power, therefore, is not only a technical question, but also a moral and political one, requiring collective responsibility. In everyday life, nuclear science will continue to expand its quiet presence. New medical isotopes promise better imaging and targeted therapies. Advanced neutron sources will probe materials for technologies from batteries to superconductors. Nuclear forensics will enhance security in an interconnected world. Even timekeeping may be revolutionized by nuclear transitions, providing clocks of unprecedented stability. Each of these advances extends the strange, that silent reach of the nucleus into practical domains, shaping daily life in ways that are often invisible but profound. As humanity confronts climate change, resource limits, and the demands of an expanding population, nuclear energy offers one of the few scalable paths to deep decarbonization. Renewable sources, such as solar and wind, will play critical roles, but their intermittency and land requirements mean they are complemented best by stable, high-density sources. Nuclear fission already provides this, and fusion may one day expand it dramatically. To reject these possibilities entirely would be to ignore one of nature's most potent sources of power. To embrace them carelessly would be to risk repeating mistakes of the past. The challenge is to harness nuclear science wisely, with humility and foresight. At its deepest level, the future of nuclear discovery is not only about power, but also about perspective. By probing the nucleus, humanity learns how the universe operates at its most fundamental level. By applying nuclear energy, humanity tests its ability to wield knowledge responsibly. The nucleus is at once a source of illumination and a mirror, reflecting our capacity to create and to destroy. In contemplating the future, one sees both promise and peril, both opportunity and responsibility. And there is an existential truth embedded in this vision. The same processes that light the stars and forge the elements also lie within our reach. The same forces that shape galaxies are the ones we now attempt to confine in magnetic fields and reactor vessels. In learning to command the nucleus, we are, in a sense, learning to echo the universe itself. That echo could sustain civilizations for millennia, or, if misused, it could bring devastation. The nucleus reminds us that the smallest domains of matter carry the largest consequences. In planning the future of nuclear power and discovery, we are deciding not only how we will live, but also how we will belong to the cosmos. Still with me, friend? If your eyes are heavy, let them close now. Your mind knows the way. If you're still awake, the next video is waiting on your screen. Let me keep you company a few minutes longer. Either way, thank you for spending your night here. May your dreams be quiet, your breaths be easy, and your thoughts drift like stardust. Sweet dreams among the stars.